Hi, everyone. My colleagues and I would like to thank you for attending my presentation about optimizing IoT blacklists. I'll try my best to make it as interesting as possible. A little bit about myself. So I'm a Bachelor of Computer Science student researcher at Stratosphere Lab at the Czech Technical University of Prague. And this research is part of the Apostomap project, which is a joint project between CVUT and Avast Antivirus. So to jump right into it, blacklists, why do we need them? In an age of machine learning and artificial intelligence, we may forget why we need blacklists and whether they're being, still used. Blacklists are still the core of threat intelligence feeds. Many companies and open source feeds will collect data from honeypots and other real devices and aggregate the attacks together into threat intelligence feeds. Very often, these threat intelligence feeds are themselves blacklists. So why do we still use them? Well, the quickest and easiest way to stop an attack is to check the source IP or domain of the attacker against a blacklist, and if it's malicious, then block it, and job done. Many antivirus software will use a quick blacklist check on a malicious connection as a first line of defense. So there are two general methods for accessing blacklists in threat intelligence feeds. The first is via download. This is a very traditional method for accessing threat intelligence feeds. Basically, the way it works is an end user will download a threat intelligence feed from a threat intelligence provider and implement it in a firewall, and therefore use it to block attacks from bad actors. Some pros to this methodology is that processing per query is very fast because the actual threat intelligence feed is loaded into memory. It's very fast in terms of processing. It's also very easy to protect several devices at once, especially if the blacklist is implemented in a firewall or a router, therefore protecting all the devices behind that firewall or router. Some cons to this is that you obviously need the memory and space to be able to store that blacklist, as well as processing power to be able to implement some sort of antivirus software. Another problem is that very often there are many threat intelligence feeds available, and it's difficult for end users to choose which ones to use. And then lastly, sometimes it's annoying to have to update and delete these blacklists because they're stored locally on the device. The second method for accessing these blacklists is via API access. So servers and connections against the database, which is stored in the threat intelligence provider's servers. Some pros to this and cons are pretty much the reverse of the previous methodology. Namely, you don't need the memory and this extra space to actually store the lists. Very often, you don't have to worry about merging the feeds together and choosing feeds or updating and deleting because the threat intelligence provider takes care of all of that for you. Now, some cons to this is that the process per IP, the querying process, is much, much slower because you're querying against a database that's not stored locally in RAM. Other problems is very often this methodology has to be implemented on a device-per-device basis, and it's difficult for verifying later. So a new problem that is being posed to both of these threat intelligence services is IoT devices. And what I mean by that is usually one of the above methods is implemented in a firewall or a router device in between these IoT devices and the internet, therefore protecting all of these IoT devices using the central router protection. Now, this makes a lot of sense because most IoT devices don't actually have the memory or storage or even processing power The problem is that due to their configuration, many IT devices are actually exposed directly to the internet. And with the rise of 5G networking, a lot of these IoT devices are going to be shipping with SIM cards or eSIM cards. Therefore, making this problem even more. And basically the issue is that with all these devices connected directly to the internet, all of the attacks are going to go directly against these IoT devices. So the problem is that it's becoming difficult to protect IoT devices using traditional blacklisting methods. So what's the problem? The problem is blacklists need to be evaluated. Blacklists, as I said before, are made by aggregating attacks into master blacklists, and these blacklists provided threat intelligence feed, almost results of blacklist evaluation, or about the methodologies that are being used to perform these evaluations. And now I say publicly available because it's obvious that blacklist feeds are being curated and evaluated by the service providers, but this is not public information. And namely, how do companies choose the size of these blacklists? What parameters are used to determine when an IP will be forgotten from the blacklist, and so on, to compare blacklist efficacy for their particular use case? Now, these problems are further aggregated by the introduction of IoT devices, namely because they can't protect themselves using traditional methods, and very often they're bypassing these traditional security measures. As of the time of writing, I know of no blacklists that are designed to protect IoT, or of any agreed upon standards that can be used to evaluate whether or not blacklists, a specific blacklist, is efficacious for IoT. Now, some previous works in academia that have been done in this regard, namely evaluation of blacklists in general, are the following. In the first paper, the authors present a methodology for aggregating lower quality blacklists together into master curated blacklists. In the next paper, the authors present a methodology for identifying malicious IP clusters with relatively high accuracy using lower quality blacklists. And then lastly, the authors present a general evaluation of many blacklisting methodologies and address the problem of lack of common standards in terms of evaluation, and or how to solve the problem of creating blacklists that are efficacious for IoT protection. So, for any kind of proper evaluation, you're going to need a data set. In order to determine if a blacklist is capable of stopping common attacks on a particular network, that blacklist should be tested against a data set of real attacks from that network. So, for example, if we want to protect IoT devices exposed directly to the internet, we should have a data set of attacks on those IoT. So, we created a data set from IoT that is directly connected to the internet, which in fact, this data set is what we use to evaluate our own blacklisting methodologies, both of which we will be presenting here. So the data set that I just mentioned, it was generated in the Apostomet IoT lab. This lab is made up of 22 devices, including smart cameras, security cameras, Raspberry Pis, NAS storage devices, Echo Dots, and more IoT of similar nature. These devices are connected to a mirrored switch configuration, which mirrors all of the incoming and outgoing traffic to a network capture server, which then in its turn captures the traffic going to and from each device specifically. All the traffic is then forwarded through our router and exposed directly to the internet. So the key thing about this setup is that it's useful because it emulates the situation where IoT devices are directly exposed to the internet, and it allows us to capture all the attacks. So now I'd like to present the attacker IP prioritizer algorithm, which is an algorithm that is meant to create a compact blacklist of only the worst offenders using network traffic captures. So in general, our algorithm is designed to intake network captures from honeypots and output blacklists that are optimized for the kinds of devices the honeypots are meant to emulate. So in our case, we were using IoT honeypots in our lab in order to create IoT blacklists. The general flow is to ingest network traffic from our lab every 24 hours into Splunk, which is a pretty amazing sorting program that we use for ingesting our data. Splunk outputs a data set of flows, one IP, and 8 features for that IP per flow. That data set is used to update an IP database made up of all the IPs our algorithm has ever encountered. Now, this database is a very important feature since it allows our algorithm to assess a malicious IP both in terms of current and past malicious activity, no matter how long ago that malicious activity occurred. This database is then fed to our rating functions, which generate a numerical value representing the importance of each IP in the database. The higher the score, the more important that IP is to block. We currently have 2 models in our rating functions. One meant to create a blacklist with consistency prioritized, and the other to create a blacklist with novelty prioritized. And I'll explain what I mean by that in a little bit. So, in general, the rating functions, as I said earlier, are really the core of the algorithm. They generate a value representing the relative importance of a particular IP for blacklisting for every single IP in the database. So if it's a database of 200,000 IPs, then it's generating 200,000 scores, one for each IP. This numerical value, or score as we call it, is equal to the square root of each of the 8 extracted features multiplied by a particular weight, summed together, and then multiplied by the output of an aging function. This aging function, the output of this aging function, is a percentage based on a variable t, which represents a certain amount of time, and x, which controls the value at which the percentage will change as t increases. Once the algorithm has generated a score for each IP in our database, it sorts the IPs from highest score to lowest, and it takes the top 20,000 IPs from the respective blacklists, for the respective blacklists. Now, this score sorting is a very important feature for users who cannot store the whole blacklist in a device that they need to protect. It allows them to take the number of IPs that their system does allow. So, for example, if the device you're protecting can only really handle 5,000 IPs, then you can take the top 5,000 IPs from this list, knowing that those IPs are the ones that are the most important ones to be blocking. So now I'm going to talk about the difference between the 2 models that I mentioned earlier for model is designed to create a blacklist with consistency prioritized and higher score consistently attacking IPs counters. In fact, my associate, Bob Ratch, we achieve this difference in this model is by altering the weight values for the scoring function and by assigning a scoring function. Namely, the t value is equal to the number of days since an IP attack last. Therefore, as long as an IP continues to attack on a regular basis, its score will not be aged and it will continue to grow and remain on the blacklist. The next model that we mentioned earlier, namely the one that generates blacklists with novelty prioritized. This one assigns higher scores to newer IPs that attack a lot. Now, therefore prioritizing intense short-term attackers, such as end-user infections spreading from between IoT devices, web servers, possibly even cloud deployments. The aging time parameter, so the T value for this function, is equal to the days since the IP first offended. Now, thus, the idea here is as soon as an IP is detected by our algorithm and assigned a score, from that time on, its score will be decreased in order to make room for newer IPs higher up on the blacklist. So now I'd like to present a evaluation methodology to help solve the overarching problem, namely that blacklists need to be evaluated. We would love to get feedback from the community on whether this methodology makes sense to everyone. So the general way that this methodology proceeds is you select a time slot window of a specific amount, namely, for example, a week, an hour, a minute, or a day, and then you consecutively choose these time slot windows. For each time slot, you acquire all the malicious traffic from the network that you're intending to defend with the blacklist, and you update that blacklist for each one of the time slots using whatever method you're using for updating the blacklist. So in time slot 1, you train your blacklist, you update your blacklist using data collected in time slot 1, and you evaluate it against the malicious traffic from the next time slot, so from time slot 2. The idea is to calculate the percentage of the malicious traffic from the time slot the second time slot window that would have been blocked if the blacklist had been implemented during that time slot. So, for example, you can calculate the percentage of the total malicious connections that would have been stopped by the blacklist. Now, this method allows you to see how effective a specific blacklist is in protecting a particular network for a certain period of time after it was generated. In step 2, you update the blacklist again using for time slot 2, and you evaluate it against the next time slot. And then for step 3 and so on, you continue to update and train the blacklist using the next time slot and evaluate it against the time slot afterwards. Thus, you're able to create, using the same methodology. Thus, you're able to create average statistics for how well this blacklist is able to perform for this particular network as time goes on. As I said before, the time slots can be days, weeks, hours, or even minutes. What you choose should depend on the type of network that you intend to defend with this list, with this blacklist. In terms of how to quantify the traffic blocked, you can calculate the percentage of bytes transferred or events that are stopped, total malicious IPs, and so on. This is the methodology that we use to evaluate our own blacklisting methodology, the attacker IP prioritizer. So we performed a 2-month evaluation on our algorithm, and we calculated the percentage of malicious packets, bytes, duration, and attacks and IPs that were stopped by our blacklist consecutively. So it should be noted here that a perfect blacklist would be one that can predict the new IPs that are going to attack in the future. However, using current blacklisting methodologies, we can only block with good certainty IPs that have already attacked in the past. Hence the reason why blacklists are not the only form of protection available provided by antivirus software. Therefore, in order to do a meaningful comparison, we tested our AIP blacklist against a blacklist that is made up of every single malicious IP in our database, so that we can compare AIP to a blacklist that would get maximal coverage of the malicious traffic without getting into new IP predictions. So it's important to point out the size difference between these two blacklists as time goes on. So as I said earlier, our AIP blacklist is a static top 20,000 IPs. So that doesn't change as the time goes on. However, our all IP blacklist grows at a linear rate as time goes on because every day new IPs are going to attack our network. So it grew, and by the end of our 2-month evaluation period, we had over 200,000 IPs in the All IP database. In terms of our evaluation results, our AIP blacklist was able to block most of the traffic that the All IP blacklist was able to, as long as the quantifier was the amount of data being transferred. So if we look here, we see our AIP blacklist was able to block over 80% of the bytes and packets that were being transferred by malicious IPs in our network. Another interesting point to point out is that the AIP blacklist was blocking less than 50% of the malicious IPs that were connecting to our network that the All IP blacklist was capable of blocking. However, these IPs were responsible for over 80% of the traffic. So these are it was blocking the highest traffic producing IPs that were attacking our network. So what did we learn? What did we need to improve? So we learned that certain features were dominating our score. Namely, our algorithm was maximizing the amount of bytes and packets that were being blocked. However, it wasn't doing much in terms of the other data features. We also learned that our aging function needed to be optimized. We noticed that there were certain anomalies where certain IPs stayed on the list longer because their score was regaining value too fast or too slowly. And lastly, we learned from our testing that our lists could be smaller. In fact, we saw that we were able to keep similar stats with less false positives with a blacklist slightly larger or slightly smaller on different days. So in order to solve these problems, in the next version of the Attacker IP Prioritizer, version 2.0, we implemented a number of changes. Namely, first of all, we normalized the input features using minimax feature scaling, thus preventing the feature domination that we mentioned earlier. In this way, the output score is equal to the normalized features multiply the square root of the normalized features multiplied by their respective weights, summed together and multiplied by by the aging function for that particular model. We also added a database to track the aging changes for each IP, thus preventing certain IPs from losing or gaining score too quickly. We also changed the blacklisting threshold to depend on an IP score being above a certain score in order to be blacklisted. Therefore, as I mentioned earlier, we used to have a static 20,000, and now the size of the blacklist will change depending upon how many IPs achieve a score that's higher than our threshold. Some future improvements that we'd like to implement in version 3.0 of our Attacker IP Prioritizer is we're working on some data analysis, comparing all of the input features together. Some new features that we'd like to implement in our scoring process are the number of attacked ports, the number of attacked honeypots. We'd like to add an ASIN database and reverse DNS data. And this is all under the umbrella of evaluation. You change something and you evaluate. If you implement a change, you immediately evaluate it using the explain methodology and see whether or not it makes it has an effect on the efficacy of the methodology for protecting our particular use case, namely in this case, IoT devices. So to sum up our contributions, we have presented a new algorithm for blacklist creation, the Attacker IP Prioritizer, which is in the form of an actual downloadable tool, open source downloadable tool that you can download and implement in your particular network. We'd like to present a methodology we presented a methodology for evaluating blacklist efficacy. And this methodology, in fact, we would like to have evaluated by the community to see what people think. We presented preliminary results of the evaluation of our algorithm and talked about future works we're going to make based on these results. And lastly, we'd like to present a curated open source threat intelligence feed for IoT, which in fact we have been publishing now for a few months. in our lab's public datasets webpage. So here are some links to the locations for our different contributions. You can find our threat intelligence feeds at the following link as downloadable blacklists. The tool that I described earlier is also available and downloadable at the following link. If you want to learn more about the Approximate IoT Lab, you can find more information on our webpage. And lastly, we're tweeting the top 10 IPs from our blacklist every day at our Twitter handle at Stratosphere IPS. And so thank you all for listening to my talk, and see you in the Hack in the Box Discord channel for questions and answers.